Good morning, kiddo Rooskies. It's time for us to do some more examples of equilibrium. So I have three examples, although one is going to be in multiple parts here, and they culminate with the most egregious example of a problem in equilibrium. So your job here is to pay attention to these and to see what is similar on our approach each time. Each one of these will teach you something. So the first example, example one, is a method to find a person's center of mass. Okay, there we go. Now we're in frame. The best technique to find a person's center of mass is to get some sort of a plank or platform long enough that a person can lay down on it. So this is going to be about 2 meters long, and it's going to have a mass or weight of 50 newtons. That's about 5 kilograms. And under each end of the platform, we're going to place a scale. I'm going to draw the type of scale you might see at the supermarket to weigh your produce. That's my favorite symbol for a scale. And what we do is we convince the person to lay down on the plank with their feet right at one end. So let's see here. We got knees, butt, back, and come around, torso, knees, and feet. Oh, and then the head. There we go. That's a person on the thing. Now the person, we don't know what the person's weight is, and we don't know where their center of mass is located. Their center of mass is probably somewhere, right about here, but we don't know where that is. Okay. Now the one thing I will tell you is that this scale reads 325 newtons, and this one reads 475 newtons. And from this, we should be able to figure out not only how much the person weighs, but where their center of mass is located. So we're going to go over here and we're going to draw ourselves an extended body diagram. It's a slightly simplified thing that allows us to locate the forces and figure out what's going on with the forces and the torques. In the day of just forces, we did a free body diagram and we had just had a dot, but now we need more. So we're going to have one of these scales is exerting a normal force up on the plank. Oh, by the way, extended body diagram, it's really important to say what you're going to isolate as your extended body. And since we're trying to find something out about the person, I'm going to use the plank as my body. That way the scales and the person all have influence on the plank. Okay, so this is an upwards normal force from the left-hand scale. 325 newtons. And this force here is an upwards normal force from the right-hand scale, 475 newtons. Now at the center of the plank is a downwards force of 50 newtons. And then somewhere here, and I'm going to just put it just to the right of the center of mass here, is the weight of the person. Okay, and so that's our extended body diagram. And from that, we can take a look at the forces. So all of the forces in the y direction are going to have to add up to 0 is our statement for the conditions of equilibrium. We're not going to look at the x direction because there are no forces in the x direction. Also, although I write this down, I don't use it this way in practice. In practice, I jump right to upwards forces equaling downwards forces. It's skipping a step of algebra. So let's do that. The upwards forces, 325 plus 475. The downwards forces are 50 plus the unknown weight of the person. Well, this is quite nice because this equation only has one unknown, and we can immediately find the weight of the person. Now, look, it's no big surprise. If we have a person laying on a plank, it's being supported by two scales. We add up the weight on the two scales. That's going to have to be the weight of both the plank and the person. So these two added together add up to 800. We're going to subtract 50 away from that, and that's going to give us the weight of the person. So the person is clearly a 750 Newton person, or about 75 kilograms of person. And now we're going to go and do the torque equation. That is I usually save the torque equation for last because it's the most difficult. Also, to do the torque equation, we're going to have to add a pivot point to this diagram. Now we get to choose our own pivot point, so I'm going to choose the left-hand edge. Mainly because I want to find out how far up the person's body the center of mass is, so that's a good origin to choose for a coordinate system. But there's nothing wrong with choosing the middle or the end, or maybe even right underneath the person's body. But I think that takes the important variable out of the equation. So I'm going to choose left-hand end. By the way, this is a choice I make a lot. And now we're going to say that the sum of all the torques has to equal 0. Again, I don't use it in this form. I don't take positive torques as counterclockwise and negative torques as clockwise, add them up and set them equal to 0. I simply say that all the clockwise torques are going to be equal to all the counterclockwise torques. Now, when I say torques, a torque is a force acting a certain distance from a pivot point. Oh, by the way, let's put our distance x here. This is the distance to the person's center of mass. So 2 clockwise torques, that is a 50 Newton force acting at a distance 1 meter away from the pivot point. After all, the plank itself is 2 meters long, so for halfway it's 1 meter, plus a 750 Newton person acting a distance x away from the pivot point. We do not need a sine or a cosine or anything fancy about this because these two forces are perpendicular to the plank, meaning they exert the full amount of torque for their force. This one is going in the counterclockwise direction, tends to spin the plank that way, so that's 475 newtons, acting at a distance the full 2 meters away. And once again, a great equation with only one unknown. Looks like we can rock this one. 50 plus 750x equals, now 475 twice is 950. So it looks like we need to subtract 50, so we're going to have 750x equals 900, and x equals 900 over 750, which is equal to 1.2, which seems like a reasonable place for the center of mass of a person to be. A person who's very nearly 2 meters tall has their center of mass above their midline, above their waist. I think for a person, your center of mass is very nearly located behind your belly button. All right, so that's a great problem. It's kind of fun. It's something you can do. I will challenge you that this process can be completed with only one scale. If you were to put a pivot point or a knife edge or something that holds this end still, and you had only one scale, it is still possible to find the person's center of mass. It may require you to know their weight ahead of time. So you would have to use that scale twice. Once have the person stand on it, second time put this apparatus together. Anyway, fun little problem, a great example of equilibrium. Now we move to problem number 2, which has 2 parts. And I call this one the Yogi Bear problem. In the cartoons of my youth, Yogi Bear was a talking bear with his companion Boo Boo, a much smaller bear, and he lived in Jellystone National Monument, which of course meant National Park, which meant it was Yellowstone. And there was a ranger. I don't know if it was Ranger Smith or not, but the ranger was in control of everything. And Yogi Bear constantly wanted to steal campers' picnic baskets. So he always wanted the picnic basket. So I'm going to use the same technique I used with my sign to hide my picnic basket from Yogi. I know I'm going to use the sign functionality, but certainly a tree branch would be the same. So I'm going to put some sort of pivot here. I'm going to have a bar. The bar is going to be 4 meters long and it's going to have a mass of 10 kilograms. I'm going to hang my picnic basket here, and it's going to be a 200 Newton picnic basket. And to support this thing, because this end right here is a pivot, is that I'm going to put a cable to a higher place in the tree or building. This cable is going to make a 45-degree angle. And what I'd like to know is what is the tension in the cable in order to support my picnic basket and the weight of this bar. So there's my setup, and 2A is part A. Find the tension. Okay, find the tension. Okay, here we go. We need an extended body diagram. I'm going to do it for the bar again. And now we're going to get the red pen and do some forces. There's going to be a reaction force upwards at the pivot. There's going to be a reaction force probably to the right at the pivot. There is a tension acting at a 45-degree angle. And there are 2 weights, a 200 Newton weight here, and in the center, a 100 Newton weight. Yeah, I took the 10 kilograms and multiplied by a G of 10 to get 100 Newtons. Okay, now we are going to have X forces and Y forces and torques. But let's be intelligent about this. There's a whole lot of unknown stuff. There are three unknowns, Fx, Fy, and T. So we're going to need all three equations, or so it seems. But if we take a look, first of all, the Y equation is not going to get us anywhere right away because there's two unknowns, this upwards Y force and the Y component of the tension. The X equation is not going to get us anywhere, or at least not right away, because there's two unknown forces, a X force this way and a component of the tension this way. But the torque equation will get us the information we need all by itself. And here's why. If we choose our pivot point to be the pivot here on next to the building or tree, these two unknown forces go away and the only unknown is tension. So if I do just the torque equation, I will get the following. Clockwise force, 100 or clockwise torque, 100 newtons times 2 meters away. Clockwise torque from this guy, 200 newtons times 4 meters away. And counterclockwise torque from this guy, T times 4. Now we need to figure out the component of T that's perpendicular, and that's going to be the sine of 45 degrees. Actually, when you're using 45 degrees, you're immune from a bad choice, but let's be realistic. Now, if you don't know why I chose sine for this, then you are not able to componentize vectors in your head yet, and that's fine. You need to continue componentizing them with a drawing off to the side until you internalize that process. It will happen for you. Okay, this is going to be 200 plus 800 equals T times 4 sine 45 degrees. So that means that 1,000 divided by 4 sine 45 degrees is going to give us the tension. And this will tell us the strength of the cable that I need to purchase in order to suspend my picnic basket safely. Okay, 1,000 divided by 4 and also divided by sine of 45 gets me 353.5. So let's call it 354 newtons. Now that's going to be the tension in the cable. I obviously don't want to go out and buy 354 Newton cable because if anything happens, dust, pigeons, anything, that is going to break. So I should buy something, in the 600 to 700 Newton breaking strength range just to make sure that my picnic basket is safe. But I am evil. And so what I really want to do is I'd like to punish Yogi Bear for his picnic basket thievery. And so I'm going to set this up so that Yogi can walk out and try to get my picnic basket, but at some point he's going to create so much stress on this tension that the cable's going to break and it's going to swivel down and dump him on his butt below the tree or building. So I'm going to choose a tension breaking strength of 1,600 newtons, and I want to say how far can Yogi get out on the beam. And so that means I'm going to let Yogi the bear walk out onto the beam a distance X, and I want to see how far he goes. Because the further he goes along this beam, the more his weight is being supported by the cable and less by the pivot point. That's just a fact of life and something we kind of proved with that scaffolding example. All right, so adding this changes this diagram a little bit. Oh, and I need to tell you that Yogi is a 1,000 Newton bear. So we have to add one more force. I'll put it out here, and it's 1,000 newtons. Okay, so my drawing is now rather cluttered and spastic. Perhaps you should make yours a little better. And we're probably, no, I think we can still get away with doing just the torque equation. So let's do it. We still have 100 at a distance of 2, that's the effect, the torque effect of the weight of the bar. We now have 1,000 at a distance X, that's Yogi's weight. And we have 200 times 4, that's the weight of the picnic basket. And over here, we have the tension, which is 1,600 times 4 times the sine of 45. So once again, this is a really nice equation because we have only one unknown. We should be able to get to an answer pretty quickly. Let me dash it out. 200 plus 1,000x plus 800 equals, now 1600 times 4 times sine of 45. 16, oh, hold on, clear. 1600 times 4 times sine 45. 4,525. All right then, the 200 plus 800 add up to be 1,000. We got to bring that over there and subtract it, so it looks like 1,000x equals 3,525. And so if we just bring the decimal place in 3 times, x is seen to be 3.525 meters. I'm evil because Yogi gets 3.5 meters out to the end of a 4-meter stick before the tension is so great that the thing breaks and dumps him on his rear end. Perhaps we could change this problem up a little bit. What if we sent Boo Boo? Boo Boo Bear is probably half of Yogi's mass. I wonder if Boo Boo could make it all the way out to the end. But you can see how the process works. And in this case, we were smart enough to, 1, choose a pivot point that gets rid of unknown forces. 2, we were smart enough to put the reaction forces at the pivot point on here. That's not something that's completely obvious to students. And 3, we were able to successfully just use the torque equation by realizing that the x and y force equations don't get us an answer right away. Okay, I'm going to cut this short because we're already at 16 minutes. I'm going to make a second video with the ladder problem.